now move to our next speaker, and that is Oliver Brand. And Oliver is a professor at Georgia Tech Department of Electrical and Computer Engineering. He is the NNCI Scenic Site Director, and he's also the director of our overarching organization, the NNCI Coordinating Office. So he has a PhD from ETH Zurich, and he also serves as the executive director for the Institute of Electronics and Nanotechnology at Georgia Tech. So Oliver, we'll turn it over to you.
Thank you, Pat. I think you can hear me already. And let's now try sharing my screen. Does that work?
Looks good. It's not full screen. Now it's full screen.
All right. Okay. So good afternoon, everyone. I mean, I understand that it's me that stands between you and the lunch break, right? So I try to keep it relatively concise. Try to give you an overview of Scenic, the NNCI site Scenic, or the Southeastern Nanotechnology Infrastructure Corridor, and then highlight a couple of nano-enabled IoT projects that we support within Scenic. So here it changes. So if we look at Scenic, we always say 3 universities, 2 locations, 1 site. So we are a partnership of 2 nanotechnology centers in the southeastern US. On one side, the Institute for Electronics and Nanotechnology that I direct myself, that is an interdisciplinary research institute at Georgia Tech. And then on the other side, the Joint School of Nanoscience and Nanoengineering, or JSNN, in Greensboro, North Carolina, which by itself is an academic collaboration between 2 universities, North Carolina A&T State University and the University of North Carolina in Greensboro. And on the right, you see kind of our 2 headquarter buildings right now. I always say they are so similar, we almost had to form a partnership. A few words about our capabilities and about our user base. So we pride ourselves to be a one-stop shop for nanofabrication, nanocharacterization needs. We support quite a broad area of expertise, and I highlight some areas here in particular, going all the way from materials, processes to devices, systems, and their applications. And maybe for nano IoT, the area, and maybe I can put that onto the laser pointer. For nano IoT, the areas that you will see the examples from: flexible variable electronics, MEMS, NEMS, sensors, and here's the buzzword IoT already. And then I have several examples out of life sciences, medicine, and health applications. Like all the other NNCI sites, we support research aligned with NSF 10 Big Ideas and other societal grand challenges. A few words on our capabilities and also staff resources. So between the partnership, we support more than 300 fabrication and characterization tools. We can support wafer sizes from 100 millimeters all the way up to 300 millimeter panels for packaging applications. You see we have quite substantial staff expertise, more than 35 staff members that support the researchers. And here you see a little bit our strength of both partners and the capabilities that we offer to users from what we call non-traditional disciplines especially. So at Georgia Tech, there is a lot of focus on top-down micro nanofabrication. In the last couple of years, we did quite some investment in the area of maskless lithography, and that can be optical lithography. But of course, in order to get to pattern sizes below 10 nanometers, we, like other sites, use electron beam lithography. Again, all these techniques are maskless, and you can change your pattern, you can change your design almost on the fly. I want to highlight that we have a packaging facility. We actually have a packaging research center at Georgia Tech that started as an engineering research center now almost 30 years ago, and has sustained a industry consortium over this long period of time. at JSNN, particular focus on 200 millimeter wafer processing, but also bottom-up nano fabrication based on material synthesis. You see some of the maybe more unique capabilities. I highlighted here additive manufacturing because I really think additive manufacturing technologies will play a key role in Internet of Things devices and applications as well. And we've done quite some investment in this area as well in terms of 3D printing, inkjet printing, aerosol jet printing, particularly keeping in mind small dimensions, right? So going below, let's say, 100 micrometer that I may be done with more traditional 3D printing technologies, all the way down to even sub-micrometer 3D printing techniques. We have kind of a goal of adding 10 tools and capabilities per year based on the research needs, and we have actually done that quite nicely over the past 5-6 years. We have a fairly large user base, and I grab my phone here to control time a little bit. We have a fairly large user base. Pre-pandemic, some 1,300 users. 1,000 of them are internal, representing more than 250 faculty groups. 280 external users, and then just a highlight of the external users over the first year of the, and for 4 years of the NNCI, and I really have to update that. We worked with 50 academic institutions, more than 150 small companies, more than 50 large companies, and about half a dozen of government organizations. You see the amount of hours that the users log into the core facilities per year, and a relatively large number of users that we train on an annual basis. It's kind of a breakdown of the user disciplines. And you see we are kind of dominated. This is self-reported. We're kind of dominated by material users, but then a broad distribution. You see MEMS, mechanical engineering, optics, chemistry, physics, life sciences, and so on. A few examples. I think I have 8 examples that IoT examples that I want to share with you, and I kind of put them into the categories of structural health monitoring, and we really haven't talked about that too much today yet. Environmental monitoring, wearable flexible electronics, biosensing, and then energy storage and power transfer. And so I'm the messenger, right? I'm not an expert in any of these fields, except maybe the example that I bring out of my own research group. I always highlight here the research group that the example belongs to, and I also provide the email address in case you have questions that go beyond my particular knowledge. So the first example is from Professor Manos Tenseris, who is in electrical and computer engineering at Georgia Tech. His background is really RF electronics, millimeter wave communication, and he pairs that with additive manufacturing technologies, particularly inkjet printing and 3D printing technologies, in order to create what he calls the Internet of Smart Skins for structural health monitoring and smart agriculture applications. This is an example of one of these flexible devices. So he calls them the smart skins, right? And onto these flexible devices, he can integrate communication capabilities, as well as sensing capabilities. So there are antennas on there, there are sensors on there, communication devices on there, and oftentimes the antenna by itself might be the sensor. Many of these devices are ultra low power, so he says in low microwatt range. Many devices are battery-less, so they harvest energy from the environment. So, for example, from 5G networks, he can have long-range communication. And the interesting thing that I found by reading some of the papers is that he can localize in real time the sensors using technologies that he is using. And I also try to always at the bottom here give some example publications where you find more information on that particular technology. The next example is again enabled by additive manufacturing. This is work out of Professor Hong Yo's group. He's in mechanical engineering at Georgia Tech, and he's working on fully portable wireless brain-machine interfaces. And again, the enabling technology that he is using for making these flexible interfaces is aerosol jet printing, and that's again one of the technologies available in the scenic core facilities. He uses aerosol jet printing for variable sensors and variable electronics applications, and you see some of these patches that you can put on the skin with a kind of a characteristic wavy metal pattern, so that they can conform and stretch with the underlying skin. I kind of found this device here interesting, which is an electrode structure that is I think it is 3D printed. That allows you to make better contact to the skull here in this particular, or the skin over the skull here in this particular case. So that is Hong Yo, mechanical engineering. The third example, I bring one out of my own research group. This is actually, I would say, non-traditional for me. I'm traditionally a silicon sensing group, but over the last couple of years, we have looked into making sensors, and these are soft sensors using liquid metal structures. And so this is an example of a wirelessly interrogated chemical sensor, where really the sensor itself is a capacitive sensor that is coupled to an inductor. This forms an LC tank, and that can be wirelessly interrogated, and you basically look at the frequency at which this LC tank absorbs energy, and the frequency changes because the capacitor, which is your chemical sensor, is a variable capacitance. Basically changes the capacitance based on the chemical environment. The really interesting thing here is that this is embedded or implemented in all soft technology, where we use liquid metal eutectic gallium indium structures for making conductive lines, right, to build the inductor, to build the capacitor, and then this is all embedded into PDMS type structures in order to make it stretchable, bendable, and so on. This is work done by PhD student Mingo Kim, who has graduated in the meantime and is actually a junior faculty member in Korea. Switching more to silicon technology, and this is work from my colleague Farouk Ayazi in electrical and computer engineering at Georgia Tech. He is known for his work on one side on inertial sensors, accelerometers, and gyroscopes, but also his work on timing devices, silicon-based. And in recent years, he has used his expertise in those areas to apply them to the medical field, and working together with bioengineers and also medical doctors. So for example, he has applied his accelerometer technologies to build contact microphones in order to look at heart sounds or lung sounds. And I think this is an example of lung sounds and particular sound patterns associated with wheezing. And on the other hand, his resonators, he has transformed or is now using as mass sensitive chemical sensors, and in this particular application used for the detection of ammonia. So this work is now funded by, you see, different funding agencies ranging from federal funding agencies as well as industry. But this is silicon-based sensors for IoT applications. The next example that I wanna bring is again in the MEMS field. This is work from my colleague Peter Heskes in mechanical engineering at Georgia Tech, who has long-standing expertise in chemical sensing as well. And he recently, in collaboration with colleagues in computing, as well as the Georgia Tech Research Institute, has applied some of these techniques to build sensors or sensing systems that allow to sense chemicals, often volatile organics that are emanated from skin. And in this area, there was recently a call for proposals, for example, from the National Institute of Health. And you see how such a system could look like in the end, right? A variable system, and then the underlying sensor in this particular case could be an ultra low power micro-machined gas sensor. Kind of an interesting application for me, but if you hear the background, it's kind of logic. It's using wireless sensor capsules for monitoring processes that go on in bioreactors. And so this is associated with what is called the Marcus Center for Therapeutic Cell Characterization and Manufacturing. And Bernie Marcus, you might know, is one of the co-founders of Home Depot. And he is funding a lot of research that affects life sciences or quality of life in the Atlanta area. But this is a relatively big center. There is also an engineering research center called the Center for Cell Manufacturing Technologies associated with this with these Marcus activities. And so here is kind of the approach of building a capsule, actually a 3D printed capsule that embeds sensor technology that can be used to monitor processes that are going on in bioreactors, process these data internally using on-chip electronics, and then having a microcontroller and a Bluetooth interface to connect the findings or the data to the outside world. This is work done by Billy D. Brown, who is with the Georgia Tech Manufacturing Institute, and Eric Fogel, who is a colleague of mine in material science and engineering. And the last two examples that I want to highlight are in the area of power sources and power transfer, because all these devices you have to power in one way or the other. The first is work from a group in mechanical engineering, again, Sungwoo Lee, who is working on flexible and stretchable energy storage devices for microelectronics applications. And you see a different variety here. This can range from paper-based flexible supercapacitors to carbon-based flexible lithium-ion batteries. This was a collaboration with my group, right, using this liquid metal technology in order to make really soft supercapacitors for energy storage applications again. And the last application is again from mechanical engineering, Levon de Gertekin, who has a background in capacitive micro-machined ultrasound transducers, so for imaging applications, and he's using these ultrasound transducer arrays now for power transfer, ultrasound-based wireless power transfer, where he uses a parametric mechanism where he can use ultrasound at double the frequency of the frequency of an RLC resonance circuit in order to power that resonance circuit. And he has recently demonstrated milliwatt power transfer using this approach. So these are the examples that I want to show. The last slide that I do want to highlight, that I just added actually 5 minutes before my presentation, is that there is a Center for the Development and Application of Internet of Things Technologies at Georgia Tech called CDITE. The webpage you see here, cdite.gartech.edu, They are less so on the sensor side, but really more on the application side and on the software side of Internet of Things technology. So I want to highlight that as well. And with that, I do want to close my presentation. So thanks for your attention. I hope this gave you an overview of what Scenic is all about, what our capabilities are, and what some of the research, Nano IoT related research is that is going on within Scenic. And so now I try to go back and stop sharing. Yeah, and I'm certainly open for questions.
Thank you so much. Yes, open for questions now. So please raise your hand or send it through the Q&A. So in the meantime, Oliver, maybe I could ask you a question. So you mentioned one of the technologies that you're using is this aerosol inkjet printing. What is that exactly? I'm not familiar with that.
So the ink is in. So my understanding, again, I'm not an expert, right? So when you look at traditional inkjets where you have droplets of the ink, in aerosol jet printing, you aerosolize the ink, right, and jet it down to your substrate. And I think with that you can do finer lines than with traditional inkjet printing, and you have also more material choices. But I am not an expert. So if there's an expert here on the call, please chime in.
Yeah, that's interesting. Yeah, yeah, and maybe the variety of materials you could use with that.
Yeah.
Do we have any questions for the speaker?
Oliver, have you seen any other emerging technologies, unusual technologies that have started to see use by this group? You know, for example, you mentioned biocompatible 3D printing of capsules out of biocompatible material. I don't know what biocompatible means in this context. It's not going in the body, but still, are there other interesting new fabrication technologies that you've seen?
Yeah, so I mean, biocompatible in this sense is that these are cell manufacturing bioreactors, right? So I think there still needs to be the materials that you're using in there still needs to be in a way biocompatible. I believe we see. So we see an uptake in these what I would call non-traditional microfabrication technologies. So we see more and more demands for 3D printing also at smaller length scales. So say 10 micrometer, say 1 micrometer. I mean, a lot of us have nanoscribe tools where we can even print at sub-micrometer, 3D print at sub-micrometer dimensions, even though at relatively low speed. We have recently seen an explosion of use of laser machining techniques for various applications, but also a lot of medical applications, stents, for example, right? What else comes to my mind? I mean, we talked about aerosol jet printing. We talked about inkjet printing. I think, Mark, do you have something particular in mind beyond that?
No, I think it's. I think the reason I'm asking this question is I think one of the things that may be of interest more broadly to our other sister sites is within this research area, which I don't think we will have any trouble convincing people is huge and growing. Are there interesting new fabrication technologies that our sister sites might want to look at? And so I'm just trying to mentally forward some of the more unusual fabrication technologies people are using. So we can think about.
So before was the question about heterogeneous integration, right? So there is quite a number of faculty working in that heterogeneous integration space at Georgia Tech, as you know, right? And they are looking on one side 3D integration, really stacking of wafers and developing technologies to 3D stack wafers, but also 2.5D integration where you might have glass interposers, silicon interposers, or even polymeric organic interposers in order to build larger systems. But these are more conventional underlying fabrication technologies.
Oh, in the chat.
Oh, for direct write lithography, are you developing these systems or leverage? No, these are commercial. So the ones that I was talking about are commercial.
Oh, sorry.
What was that, Pat?
Could you read it one more time? I think it's because I don't think everyone could see that.
Oh, okay. For direct write lithography, are you developing these systems or leveraging the commercial systems and prototypes being developed by others? Yes, we're using commercial systems here. For optical lithography, we particularly use Heidelberg MLA systems for direct write lithography.
Okay. I think we're at lunch break. So
yes.
Thank you so much, all of the speakers. And we have 3 more presentations this afternoon, so please come back. We will be starting exactly at 1:30 p.m. Eastern Daylight Time. And thank you all for attending, and I'll see you in a little while.